All right, so we got a couple more radioactive decays. And just showing some differences in units here. All right, so this is ancient. Here is its decay rate. We want to know how old it is, and this is the normal decay rate in living organisms. So if you're going, I don't know what to do, you haven't shown us this whole unit thing yet, don't worry, the units are going to cancel. It's a ratio. Okay, so I'm going to save us some time because we remember that K for carbon-14, I'm going to round to 1.213 times 10 to the negative 4 per year. If you don't remember that, look in your book, look in your notes, reference it. We did it in number 17 on the practice problems as well. So I'm going to just jump right in. So at the time t, look, all these are going to cancel out, all these units. So just keep the numbers. Okay, equals negative K, that's per year, times T. Okay, so here we go. Natural log 0.85 divided by 15.3 divided by negative 1.213 10 to the negative 4. This is really old. And so 23,828. Some of you may prefer to round. That's great. Remember that the limit on carbon-14 dating is around 50,000 years. So here we're going to use, you'll need to reference your notes here because I did not give you the half-life or the K in this particular problem. But so here we're going to use uranium dating. So here's its mass ratio. And it didn't have any of this at the time of its formation. So the first thing we need to do is figure out what K is. So let me tell you, the half-life of uranium-238 is 4.5 billion years. So that's a lot. So to find K, that's going to be 0.693 divided by 4.5, a billion, 10 to the 9th years. So this is going to be really, really, really small. So 0.693 divided by 4.5, 10 to the negative 9th. No, not negative 9th, positive 9th. There we go. 1.54 times 10 to the minus 10 per year. All right, now, the way that we're going to measure this is we're actually measuring rate of appearance of lead because it doesn't give us how much uranium is disappearing, but rather how much lead is appearing. So originally we didn't have anything. It was all uranium. So now we had a ratio of 0.145. And if you go, okay, this was all uranium, no lead, because originally it would have been what, 1 to 1, 0 to 1. So you just need how much you have now. So this is in at time t equals negative K 1.54 times 10 to the minus 10 per year times t. so let's take natural log 0.145 divided by negative k. 1.25 times 10 to the 10th. So that doesn't really mean a whole lot to me, but you can kind of do a quick little conversion if you want, and you can say, well, 10 to the 9th years is 1 billion years, if you prefer that. And when you do that, that tells you it is 12.5 billion years old. Both of these are the correct answer, but some of you might prefer one notation over the other.